Hey guys, hello everyone, welcome to Light the Deep. For the last 10 years, we've been building artificial intelligence using one very specific blueprint. We thought the recipe was very simple. Make it the model bigger, feed it more data, and give it more chips, as in GPUs. But in 2025, that recipe stopped working. We hit a wall. To understand why, we need to look at how we got here. This isn't just a history lesson, it's a story of how we taught machines to think. It all starts in 2017. There was a big bang. Google had just released a paper called Attention is All You Need. Before this, AI could read sentences like a human, word by word, token by token, left to right, and the transformer changed that. It introduced self-attention, and suddenly a model could look at an entire book all at once, and connect word 1, which is existing on page 1, to word 100, which exists on page 100, all at once, parallelly. So that's what gives you ChatGPT as it exists today. In 2018, OpenAI took the architecture and told, oh, this is too complex. Because Transformer had initially two architectures, the encoder and the decoder. The encoder encodes the user's query into a latent space. And the decoder takes this latent space and predicts the next token. The encoder which you will use to encode the latent space, GPT thought, hey, that is just something that's not really required. Let's go with one thing. We just train the model to predict the next token directly on user query. How will this work? And they proved something that's absolutely incredible, that you don't need to really teach AI on specific tasks, that if you put the entire internet corpus data to it, it is able to learn specific tasks like translating French, summarizing text, sending emails, so many other things. It just learns those skills by accident because of the data that you gave it. Next, we go to 2020. This is the era of scale. GPT-3 was just released. It had 175 billion parameters. For context, any model that had come before it was maximum of a few billion parameters here and there. We are talking about hundreds of billions of parameters here. 175 billion to be exact. 175 billion, it proved that size just matters. The models got bigger, they didn't just get better at grammar, they got better at reasoning, tool calling, all kinds. They could code, they could do math, they could reason, they could do something that they were never programmed for at a very, very accurate pace. And then in 2023 comes the chat era. Everybody starts using ChatGPT. ChatGPT gives in a public API due to which there was a spring of AI apps which literally transformed the world to how we see, and everywhere here and there all AI slop also got in. Yeah, all that happened. And then RLHF also happened. RLHF is reinforcement learning with human feedback. Basically you tell ChatGPT saying, hey, if it says 2 plus 2 is 5, you say, and then you make ChatGPT understand, hey, so I'm wrong. So 2 plus 2 is not 5. So I mean to correct myself that 2 plus 2 is 4. And it goes and reinforces itself to understand that 2 plus 2 is 4 and doesn't commit the mistake again. Basically, it improves whenever you ask a query and you give the feedback. So and in 2025, now the party is over. We realize that standard transformer has a fatal flaw. It gets exponentially expensive the longer you talk to it. Basically, the context is exponentially equivalent. That the cost is exponentially costing per the word that you're going to see. So we stopped building pure transformers. We started building hybrids. Frankenstein monsters that stitch together different type of math and achieve the laws of physics. Let's see how they work. So what went wrong? Why isn't attention all we need anymore? It all comes to two major bottlenecks. One, the quadratic problem of cost. Basically, let's take an example. Let's say you're in a cocktail party and there are 4 people. It's easy for everybody to look at everybody else. But what if there are 1 million people? It is tough for you to look at anybody else, forget everybody else. In the standard transformer, every single word that you type has to look and calculate its relationship with every single previous word that you had typed. So if you type 4 words, it's going to look and calculate this relationship with 16 times, which means it is an O of n square relationship, which is going to be quadratically increasing. Therefore, if for a 100-page book, it is fine. For a code base of 1 million lines of code, absolutely impossible. Math goes phew. So then, what is the second problem? Now comes the second problem, that is disk space. That is VRAM. So there's something called KV cache that your LLM uses for it to regenerate already calculated tokens. And this explodes as well. So your GPU RAM just fills up very fast for the existing model. So therefore, the AI has to remember the math it did for previous words so that it doesn't do again. For this, the KV cache, if it explodes, the model doesn't load enough. That's it. So your disk space is now limited. So if you keep on shuffling papers, you spend a lot of more time shuffling papers than you doing things on the paper. Similarly, the GPU is going to spend more time shuffling things out in and out of memory than doing real operations on the LLM. So it makes the LLM also slower. So the actual bottleneck is not the compute, it's the VRAM. So now how did engineers solve the problem? So then engineers started looking for shortcuts. The first big shortcut is called grouped query attention. Now let's take an example. Think of AI heads like different people at a conference trying to find information. In the old system, multi-head attention, that is, every person had their own complete set of nodes, key and value that they would individually search. That was a lot of redundant paper. Imagine each of the 100 people having their own set of nodes, like it's going to be 100 nodes into like so many pages, which is of waste paper. So now GQA says, hey, why don't 8 of you share one master set of nodes? They are all going to reference a single shared document which saves massive amount of energy and memory. About 85% of memory is going to be saved. But without slowing down how fast they are going to find attention. But what's the downside? Now, if the 8 people sharing the same memory, you cannot expect all of those 8 to accurately enter whatever they want inside the nodes. So they might miss a few. So this is the only pain point, that is a slight dip in the accuracy of the query attention. If you look at the code, it's a very simple trick. We shrink the key and value layers, and then during the math step, we just broadcast the data for everybody to share. That is math computation, matrix multiplication. Now let's go to the second way of solving problems, and personally this was something that really caught into the trends of AI, and it made everybody look at, hey, oh wow, that kind of moment. This is mixture of experts, and it's even now trends whenever a model with mixture of experts releases in Hugging Face. So again, what does this fix? So it fixes the speed problem. So what it exactly does is, imagine you have a hospital with 1,000 doctors. When you walk in with sore throat, you don't need all the 1,000 doctors to examine you at the same time. That would be very slow and inefficient. You only need a general practitioner to route you to the ENT specialist. Just one router and one specialist. This is what MOE basically does. It has a router in front with all specialists there. So whenever you are given a query, the router gets the top 2 experts that need to be selected that correspond to the query. And then only those 2 experts are run, and then the output of those 2 experts are given for the query. So this allows us to build models that are incredibly smart, because they have a very high parameter count, but run incredibly fast because they have very low number of parameters that are actively pulled, because you are only using few number of experts each query. Now look at the code. In the code you can see the router is just a small layer that makes the decision which experts handle which query. That's it. It's very simple, and then just the query is going to get activated with the certain FFN. That is, FFN is going to be the specialist in this case, and then the specialist is going to give the answer. See, till now we were only looking at optimization, right? We were only looking at tricks and nick and quirks on solving how better can we make the attention mechanism. So we were just doing some kind of optimization, don't fix something that ain't broke kind of stuff. So till now there was not much of architectural change. But now when DeepSeek came along, they changed the entire architecture itself. They looked at GQA and said, hey, but we are losing much detail there. As I said before, GQA had one flaw, that is the precision of some nodes are going to get lost. That is, some kind of precision is getting lost because you're going to share the query and stuff with 8 attention heads. So then they came up with something called multi-head latent attention or multi-latent attention, which is basically low ranking the attention, compressing the stuff, compressing the whatever nodes that you have and then sharing it across. So whenever you have a lot of files, you compress the files and share it across, and whenever necessary you uncompress it and view whatever you want. That's exactly the idea here. If I have to go somewhere else, I'm going to if you have to giving a machine learning example or a deep learning example, I might give LoRa. Basically what you do is you compress you represent the entire set of weights of a LLM with a small low rank matrix, a low dimension matrix, and then you only train this low dimension matrix and then call it a day. You don't do the for entire stuff. That is called LoRa, and that became very popular fine-tuning method for fine-tuning LLMs. Now similarly this latent vector, which is going to be downsampled and then upsampled only when that is mathematically required. So the only downsample vector is going to be stored, which reduces your memory cache and your VRAM usage. Now what does this give? This allows DeepSeek to fit in a context window that is 10 times larger than its competitors in the same amount of memory. Basically, DeepSeek having 671 billion parameters can fit into something which Llama 70 billion struggled to. So as you can see in the code here, the self.down compresses the data to store it, the self.up decompresses it only in the case to use it and then throws it away. Now DeepSeek did another thing, that is they thought, see, MOE is all fine, but MOE has also its flaws. What is the flaw with MOE now? See, whenever one expert is going to activate, that is, let's say it's a math expert and it knows only math and it was trained on math data sets, we don't have any guarantee that it will answer in proper English. And if it doesn't answer in proper English, then the presentation is going to be bad and the answer finally may end up being bad. So what is the use? So we need a basic expert who can handle the basic things like understanding English, understanding what the question means, understanding how to articulate the response, understanding what to think, understanding where to put is, where to put the, all of these things. And we need obviously the specialists to really do what the job they are doing. So we want to have a person who's always activated so that the basic thinking memory and the basic intelligence is always active. So that's what DeepSeek told. So they have a shared expert that's always activated, and then they have the different set of experts which are activated based on the query. Now if you see the code, you can see it's a simple code addition. Output has a shared expert extra and then it's routed to the other experts. But this stabilizes it a lot. Now whenever there is some kind of big things happening in the industry, Google comes in. And when Google comes in, things get spicy. So when DeepSeek was compressing memory, Google told, hey, do you think a word at the end of the book really needs to know the word at the starting of the book? Is that really required always? I don't think so. I don't think most people of you would ever remember the first word of the book while reading at the last page. So then they introduced something called sliding window. Sliding window in the sense you only know some things around the surrounding of yourself. That is basically they try to imitate the human. Human only remembers the last 24 hours if I asked you right now. So they have a 1024 sliding window that slides around as you go and then only those 1024 tokens is available as attention. So you only know how to attend, you can only attend to those 1024 tokens. The others are lost. Now this makes it from quadratic to linear. But the problem is, now at the last page, how do you know what is the name of the hero that appeared in chapter 1? Now this is where Gemma told we need a hybrid person. We need another person who can do it for everything. Do it end to end such that that guy can understand from the first page till the last page. So now, but we need to have very less number of these so that we can save memory. So what Gemma essentially did is, for every 5 people who had this local sliding window attention of different window sizes, they had one global attention who could read from end to end, therefore making it easy. therefore catching up with the memory, and every time the global memory will sync with the local memory, and the local memory knows details about things that haven't happened before but up to a certain limit, and then it really only attends to the local 1024 or some x number of window size context window. Now if you see the code, this is where you see the sliding window. There's a matrix, and then there is a sliding window over here. That's a diagonal. So anywhere before the diagonal and after the diagonal, 1024 tokens are able to be accessed, and these 1024 tokens is only the tokens that is going to attend to, and this makes it efficient. And okay, Gemma did something, but the boldest move of 2025 is the return of an old idea, something that transformers killed. That is called recurrence. Do you remember the term that transformers killed RNNs overnight? Yeah, but the same RNN is now helping transformers become better. So we call this linear revolution because recurrence is linear in nature. So transformers kept a perfect photograph of the past. It was perfect, but it was very expensive to store, as in a photograph. Now, state space models like Mamba act more like a diary. Instead of keeping raw data, they upload a running summary, which gets a hidden state which gets updated every single time that it passes through a neural network. So it writes like, today I went to the store, and when new info comes, they update the summary. This means the memory usage is constant, whether the book is 10 pages or 100 million pages long. The summary takes up the same exact space. This allows for nearly infinite context, but it has a downside. As in RNNs, it has a downside, vanishing gradients. Basically, it can lose some data as summary goes on. So something that has happened long before is lost, because as you keep on summarizing one thing again and again and again, over and over again, information gets reduced and over time lost. So basically, you might forget what shirt you wore to the store, and this is called the recall problem. Now, Qwen3 next solved it with gate at delta net. Just guess what it might mean. Okay, with RNN, what was the solution? LSTM. So what do you think will be the solution with gated delta net? LSTM plus transformer. Basically that. So they treat memory like a database. They use a forget gate, LSTM forget gate inside it, and the input gate and the output gate remain the same as in the transformer. The model learns exactly what to write down in the diary and exactly what to erase. This is the programmable memory system of LSTM plus the transformer for its intelligence. This broke the Qwen model, and I think till now it has been one of the most intelligent model that I have tried. Now, but the Qwen has one small problem. Basically, it can either tear down one page, that is erase information from one page directly, or keep the entire page intact. This is a problem because a page is a lot of information. There might be information that you want to erase only within a page, just that information want to be erased, and you want to retain something that is inside the page also. So at these problems, you either lose the entire information or you have the entire information, which is still bad. So Kimi told, why retain it at the page level? Make it even more granular. Make it even more precise. Let's introduce channel-wise gating. Instead of forgetting the whole memory, it can choose just specific details. Like just forget the color of the shirt, but remember who was wearing it. Like granular control allows these efficient linear models to finally compute with the transformers on hard reasoning tasks. And finally, we had to fix the training stability. These new architectures were too complex, and training them was insanely difficult but also very expensive. So you cannot afford to fail. And so you need to have very good success rate with them. So now, what did our engineers think about? So then came a model called Olmo, which went retro. They brought back an old technique called post-norm, which we used for LSTMs, GRUs, and the likes of them. It is basically the idea of placing the stabilization layer after the feed-forward network layers, rather than before it. Normally, in all the GPT and the llamas and the likes of it, you place the layer norm or any other norm before the feed-forward network. But the problem with this is the queries and keys were multiplied, and as the model gets smarter, these numbers get bigger and bigger and bigger, and they start shouting at each other. And when these numbers get too loud, the softmax function stops working because it gets maxed out. And then it only outputs either 100% or a 0%, and the model becomes arrogant, it stops considering subtle relationships, and crucially, it stops learning. So basically, you are making the model not learn. And because of this, the model's smartness is limited that you can achieve. So what QK norm is the things that they achieve, the Olmo model also came up with to introduce after the feed-forward network. The Olmo simply does a very small thing. It normalizes the queries and the keys before they multiply. So it acts like automatic gain control on microphone. It keeps the conversation at steady volume, ensuring the model stays humble enough to keep learning even at massive scales. Basically, it's going to make normalize the queries and keys. So when there are very big number, it's going to normalize them to 0 to 1 or some fixed scale. So always they are at a fixed scale, which means they can never keep shouting, which means they cannot explode. So this makes the Olmo's QK norm very stable and work well even at the post norm level, and this makes the training very stable and achievable by even normal people. Now what can we do for speed? Because speed is a very bad thing, because nowadays people want their responses like this, like at the speed of what maybe ChatGPT is generating, or because they have a lot of GPU clusters around in the globe, they are able to generate at speeds that normally you would not be able to do in your local system. But we need that speed, because whenever we need to show it to people, they want to see the speed in it. They want it to be in fraction of seconds, and they want it to be fast. So now we come up with something called multi-token prediction. Now old models were like slow type bits, one token at a time, or maximum one word at a time. This is too slow, and if the model makes an error once, it never checks back on it, because after the token is done, it's done. Now MTP models are trained to guess the next 4 to 5 words at the same time. Now what does this do? This forces the model to plan ahead of the time and makes the model define the route that it's taking. And when it comes in the position to generate the specific token, it is already having a draft of what it has taught to generate at that space. Basically, if you are going to generate 4 tokens at a time, and let's say we have a slide length of 2, that is you're only for the end user you are generating 2 tokens at a time, which means you're overlapping twice on the same token spot. So you're thinking twice on the same place. So you are more possibly accurate on generating information than a model that only looks at that place once. And therefore, this is like autocomplete on steroids for the LLM, and this makes it more accurate and more faster. What are we looking at LLMs while heading into 2026? It's no longer just a transformer. It's a sophisticated and specialized stack. We use MLA or sliding windows to fit massive memories into small chips. We use MOE and shared experts to make them huge but fast. We use linear layers to scale to infinite lengths. And we use MTP to generate text at lightning speeds and reinforce on them. Now, at the end, we have moved from the era of brute force to era of precision engineering. Now, let's see what's the final take on this. The transformer is dead. Long live the hybrid of transformers again. So the hardware didn't change, but the blueprint have been completely rewritten, and this has become the new standard. Thanks for watching.